All right. So last lecture, I talked about fully automating the bisection method and false point method. I'm going to actually do a demonstration of that first, so that if you see the process, you would automatically kind of figure out what went wrong. If not, we still can look at yours, at least a few of yours. All right. So now, yesterday I had a chance to do this because a student asked, they had some question. So I'm going to use that example and try to show you how we fully automated it. Okay. So here is the root. Oops, sorry. What am I supposed to do? All right. So here is the root. We started with an initial guess of 0.5 and 0.6. That is, we said the root lies between 0.5 and 0.6. And we calculated the midpoint after each iteration. And eventually you can see that the root converges to a value something like 0.5671 to 4 decimal points. I'm going to walk you through that process, okay, from the start. Now, first thing is, when you are having the bisection method, okay, it's bad. Al Hassan, can you please get me a marker? Yeah, sorry. So when you first start the bisection method, what do you need? You need to guess the range in which the root is found. Root could be found, right? And how do you do that? You first identify a lower limit where the function has a certain value, and an upper limit where the function has a certain value of the opposite sign. That is, if this were negative and if this were positive, then the implication is the root lies between lower and upper. Are you with me so far? Right? So how do you figure out, if you have to automate it, you can't sit there and make decisions. How do you automate the decision process? You calculate the value of the function at the lower and the value of the function at the upper. And if they are of opposite signs, how do you detect that? How can you write a statement that says, thank you so much, that says the value of the functions are of opposite signs?
Whether the product is positive or negative?
Whether the product is positive or negative. So if I write x lower and write x upper, and suppose the function looks like this, I have f of x lower and then I have f of x upper. If I write, or if I calculate the product, f of x lower multiplied by f of x upper, if this product is negative, that is, if they are of opposite signs, then the root lies between x lower and x upper. If this statement makes sense to you, we are just going to apply this repeatedly after each iteration. Okay? You're with me so far? So now I am having my equation. I'm trying to solve x minus e power minus x equal to 0. This is my f of x. Okay, and I'm going to say my x lower value is 0 and x upper value is 1. These are guesses that I came up with because I used previously the graphical method to see where the curve intersects the axis. Okay, you can, just for argument's sake, make this minus 10 to plus 10, which also happens to contain 0 to 1 and the root. So you will find out that the method will work no matter what your initial guess is, provided it satisfies the condition f of x lower multiplied by f of x upper is less than 0. As long as this is satisfied, any guess will work. Okay, so we'll start with 0 and we'll say 1. Okay, I'm just going to go with 0 and 1, and later we'll do other guesses. So you can see here f of x lower. I calculate here. You don't have to write this down or do this with me. I'll give you time. Just watch and learn. f of x lower is x or d3 minus exponent of minus d3, basically treating this like x, and f upper, okay, I'm just keeping it short, f upper is the value of x being 1 minus exponent of minus 1, that is 0.6321. And the bisection method is just taking the midpoint of the two. So x midpoint, I'm going to call this x midpoint, okay. So whatever xl is, whatever xu is, I'm going to say their midpoint is xl equals, xm equals lower plus upper divided by 2. Lower plus upper divided by 2. So that is midpoint. The whole point of automation or programming is not to commit yourself to specific numbers, but to symbols. You write midpoint is D3 plus E3 divided by 2. Whatever D3 and E3 is, you will be able to get the midpoint. What is the midpoint of 0 and 1? 0.1. And then what is the value of the function at that midpoint? That is also now relevant. What is f of xm? That is an important thing that we need to calculate. You can simply do that. X minus exponent of minus x. H3 minus exponent of minus h3. Is it making sense? Thinking about lunch already? I know I am, but then, yeah.
See, when we got to that point, I was thinking that we were gonna use G3 and F3 to kind of just do the same.
Yep, that's what we are going to do in a few minutes.
Okay.
Yeah. So now you have three values, lower, upper, and midpoint, and the corresponding functions f lower, f upper, and f midpoint. Okay. Now, here, according to my picture, here is f of xm. Okay, here is the value of the function. Okay, you can do this very simply. If f of xl multiplied by f of xm is less than 0, what does that imply? If these two are of opposite sign, what does that imply? There is a root between xl and xm, then I'll write x lower nu is simply the same x lower, whereas x upper nu is now xm. That is, you don't need this because you have narrowed down from x upper to xm. Your root is here. This portion is totally not relevant at all anymore. So you're just replacing for the next iteration, the new value of lower still is the old value of lower, but the new value of upper is now xm. Okay, that is if this is true. As it happens with any if statement, there is also a case where what if it is not true? If this is not true, that is, if this is true, you do this block. Else, the other possibility is if this is not true, it can either be 0 or positive. Then, if this is this, if suppose these two are of the same sign, then xl nu would be equal to xm, and x upper nu would be the same x upper. In that case, although my picture doesn't say that, this portion becomes irrelevant, and you now moved your lower to here instead of moving the upper to here. Yes.
So for the first part, are you saying that if f of x lower and f of x midpoint are both less than 0, then it would be x of
Yeah, you are bringing this here. Just speak visually. You are bringing this here and squeezing the range like this. If it is the other way, you are bringing upper here and keeping lower the same. Actually, I misspoke, sorry. If this were not true, what you're doing is keeping the upper fixed, but eliminating this part and bringing the lower to the towards the middle or to the middle. Okay, so now let's implement that here. You have the first line already done, and I have f lower multiplied by f midpoint. Okay, this is what I need. Now to get my next statement, I'm going to write if this product f of x lower multiplied by f of xm in my spreadsheet, that is J3. That is J3 right here. This is in my spreadsheet, J3. Okay, if J3 is less than 0, if J3 is less than 0, what if J3 is less than 0? What should I do? Excel new is the old Excel. If it is false, Excel new is XM. I need to put that into my sheet. Excel new, what is the new value of Excel? Should be the old value of Excel. If it is false, then it should be the midpoint. See? Because this product is let me see. Yeah, that is this F lower and F midpoint have the same sign. So actually, in our case, this is not getting activated. This is getting activated. Okay, so we are getting Excel new is the midpoint. And what about the upper value? Actually, I should have put it here. Sorry. Yeah. And what is the upper value if J3 were negative? If J3 were negative, what is the upper value? Is the midpoint. If J3 is positive, it's the old upper value. If J3 is negative, that is my if statement. That is the logical test. My logical test being whether J3 is negative. If J3 is negative, X upper is the midpoint. And if it is false, it is the old value of upper. Take a minute and think about whether you understood this implementation. Take a minute, think about it. If you are not sure, please ask questions. Yeah.
What? Were you not putting it in the f of x lower and f and f?
I made a mistake. I should have put it here, not put that.
And
Try punching this and see if you are able to actually get Excel to give you 0.5 and 1 instead of you entering it. If this function, if J3 were less than 0, for lower, I'm implementing this line and this line. If J3 is less than 0, then the same lower. If J3 is more than 0, then midpoint is the new lower.
go for one box.
Sorry?
You go to E3. You're at E4.
Okay. I mean, you have to actually try this in order to say if this makes sense to you. It will all look like it makes sense right now, but later you might not see it that way. So, if you don't have your laptop with you, at least try it on pencil and paper as best as you can. That's at least will help you register the method. Okay, so what do you do about the next lines? Can I just copy paste this? Because this is Excel, it will allow you to just copy formulas line after line, just drag it down. So I have my new lower, which is 0.5, and the value of that function at that 0.5 is minus 0.1. At 1, it's still the same value, and the midpoint of 0.5 and 1 is 0.75. And the value of the function at this midpoint happens to be 0.277. Quick question. You look at 0.75, it's between 0.5 and 1. You look at the corresponding function values, minus, plus, plus. Intuitively, tell me where the root is. Is it between 0.5 and 0.75 or between 0.75 and 1?
First one.
Between 0.5 and 0.75, right? Because negative, positive, positive, positive. So the root is between 0.5 and 0.75. So if the next iteration gives you something that contradicts that, it means you have made a mistake. You should know when you are going on the wrong track. That's also important. All right. So now, actually, you have solved the problem. If you have written this line, that means the problem is done. If you have done it correctly, all you need to do is drag it down to several lines. And let's do that. So third iteration or second iteration. Wait, something is not right here.
I think it was supposed to select midpoint, but it selected upper.
Oh, okay. It was supposed to select J3. Okay, F. It was supposed to select. Yeah, sorry. Should have selected this. And it should have selected. Yeah, this is correct. So now if I drag this down. So focus on this column. Okay, focus on the column H. I went from 0.5 to 0.75 to now 0.625 in 2 iterations. Okay, let's drag this down more. And my midpoint value is getting more precise, 0.56, 0.59, 57, 57. So it's getting more precise. And if I add more iterations, I'm getting 0.566, 568, 5683, 5673, 5668. It's getting there, it's slowly converging. But the thing you need to focus on is what's the value of f at that midpoint? It's already minus 7 times 10 power minus 6. It's practically 0. Suppose we set a tolerance of 1e minus 6. That is, you want to keep iterating until this value, column I, falls below 10 power minus 6. You need to do this for a few more iterations. And if you see here, after 19 iterations, the value of the function has dropped to below 1e minus 6. And if I set my tolerance as that, that means after 19 iterations, we have converged. Do you see this? Or do you not sure why we are stopping at 19 iterations?
I'm not sure why you stopped.
I'm stopping because if I look at the value of the function, look at column I, that is the value of the function evaluated at the midpoint, at my root. And that value has now come to 2e minus 7, which is smaller than my chosen tolerance of 1e minus 6. Or the absolute value of this, I want it to drop below 1e minus 6. That's why I'm stopping at 19 iterations. Just to contrast, bisection method for the same problem for the tolerance of 1e minus 6 converges in 19 iterations. Remember the number 19. Okay. You go to Newton-Raphson. The same problem or the same same problem converges in only 2 iterations. So in terms of speed, you can already see Newton-Raphson performs much better than bisection method. Okay. Let's take a small pause, and I'm ready to take questions from you if you have any questions related to implementing this bisection method and automating it. Go for it. Yes.
Is there a reason why you did not use your column?
Yeah. Good question. So you can do the same implementation without looking at the product of lower and middle. You can implement the same problem by looking at the product of middle and upper. It won't change one iota. You can do the same implementation except if middle and upper were multiplied, the scenario will flip.
Okay.
Because now you are looking at it from the other side.
Okay.
That's all. Except that there is no other conceptual difference.
Okay.
Other questions?
Would we need to show both? Would you want to show?
No,
both
no.
sides or just one side or the other?
If you can handle one, I trust you to be able to handle the other also.
Okay.
Yes.
Were you looking for this exact way to do the bisection?
Is there any other way? If you can show me, I would accept it.
I have a different.
Yeah. Can you share your screen?
Do you want me to join the?
No, yeah, join the Zoom. Yeah. You were saying something?
Yeah, I also, it sounds good as that.
Yeah. Can we, yes, see. Other questions? Now, what is the difference between this bisection method and this false point method? The only major difference is the way you update your x value in bisection method, you just take the midpoint without thinking much. In the false point method, you use a formula which I've already punched in here as x lower and x upper and involving the function values and the slope. Okay, so can you now try automating this false point method? If you don't have a spreadsheet of your own, just go to the Canvas page and you can download this. This is right there. You can already download and start trying. All right, so Omar, maybe you can share your screen. We'll come back to this false point after we have seen a few implementations.
Oh.
Not able to share screen?
I need to give Zoom access. I need to restart
Can you
Zoom.
please mute your computers? Yeah, you can share screen. I have given permissions to everyone to share. Can you try, Stephen?
Trying to find it. Using the link file.
Okay, we'll come back to this. Okay, so let's talk about similarly automating this false point method. We'll come back. False point method. First thing, the only difference between bisection method and false point method is the way you update the next value of x. Is that okay? Is that something you could agree with? Because if you see here, the next value of x is updated using a formula, whereas in bisection method, it's simply the midpoint, no questions asked. You still do the same thing. You check whether the root is between the lower and the next value of x, or between the next value of x and the upper values. We'll do the same checking. Can you try implementing this here? It's practice. I know most of us won't be able to do this at the first time, but that's okay, practice. Try, get stuck, call me. I'll give you 2 minutes to either open a sheet and get up to here. Okay, and get up to here. Or you can go to Canvas and download this module 1 examples file and go to the sheet called false point, and then we'll do this together. Do either of the two in 2 minutes. I'll give you both of you a chance to show your screen. Wait. Those who don't have your laptops with you, I don't see many of you. Please bring your laptops. You need to participate, and this is where I'm going to award you score for class participation. One more minute, and then we'll start. Are you able to download and get here and ready? Be ready. Are you ready to do this with me? One step at a time. All right. So now I have f, the function evaluated at the lower, the function evaluated at the upper, and the function evaluated at the new value of x. Okay, so I'm going to add the annotation. This is new x, okay, and new value of the function. Okay, so now I want to implement this. Except whatever we call midpoint, we'll call it new now. Okay, there is no other difference. We still want to implement this block in Excel. Okay, so what do? If you're going to tell me, one of you is going to actually tell if what should I check, or what should I actually do before I check? I need to multiply f lower multiplied by f new. F lower multiplied by f new. Now one of you go for it. If J3 less than 0, what if that is true? If J3 is less than 0, what should I do? Lower should be same lower. If not, lower should be the new value of x. Okay, is everybody seeing this? Not, please don't feel shy. Just say, can you explain this in a different way? Something like that. Or what the heck? All right. You can, if J3 is less than 0, then the new value of x is the same as the old value. If not, I'm sorry, if J3 is less than 0, the lower remains, hard to see from here. The lower remains same. If not, it flips to the new value of x. Okay, and for the other one, for the upper, if J3 is less than 0, what happens? Look at these two lines. If J3 is less than 0, new value of upper is the X new. Otherwise, it stays the same. New value of upper is,
Use the box.
sorry,
You get the box still after that.
Yes.
H3. Oh, sorry, yes. Thank you.
I have the memory of a baby. So if J3 is less than 0, then what happens to X? X upper is the new value of X. Okay, I'll do one information at a time. Is the new value of X. If not, it's the old value. It's the old value of X. The rest of it is just something you can copy paste. So what's going on here? The value of the function at the new value was 0.07. It's dropped to 0.007. If your tolerance criterion is 0.01, you're already there. Okay, except we'll do 10 power minus 6. So let's do a few more iterations. And before I do that, are you cool with it? Can I drag this to a few more iterations? So I'm getting the new value of X to be 1.34 times 10 to the minus 7, which is lesser than my tolerance of 1e minus 6. So I can call this criterion met, or in other words, the absolute value of F nu. The absolute value of F nu has fallen below the chosen tolerance of 1e minus 6. All right, so time to make a comparison. Same problem or the same equation, f of x is defined as x minus e power minus x equal to 0. We have our bisection method, and we have our false point method, and Newton-Raphson, and what else? Secant method. Secant. In this unit, we also have two other methods, that is graphical and single point iteration. Single point iteration. I've already told you, use the graphical method to find the interval where the root may lie, kind of like a first pass method. And I've asked you to do self-study this. It's not a very interesting method, or not more interesting than these. So how many iterations did it take to do to get to the for the error, or for the function value, to fall below the chosen tolerance, which in our case is 1e minus 6, or I'll say 10 power minus 6. But bisection method took 19 iterations. Okay, we saw that 19. False point method took 6 iterations. Newton-Raphson took 2 iterations. And we also have the secant method, which we did the other day. It took 3 iterations. So in your homework, there is a word problem that asks you to do some physics steps at the start. once you arrive at the equation that needs to be solved, that might look like this or looks like something else, but it's an equation that is of the form f of x equal to 0. You are going to take these methods, apply all of them to the same problem, choose a tolerance that is appropriate for that application, and then make a comparison. How many iterations did each of them take? Is that clear? How you want to present your answer? Yes?
How do we know, what's an appropriate tolerance?
So if you are not sure in a particular situation, you can think about the quantity that you are trying to, this is just general guidance. The quantity that you're trying to calculate, say for example, is a velocity. If you go and try to make a velocity measurement, you need to do some homework on with what accuracy is it generally possible to do velocity measurements. Can you get it down to 1 decimal point? Can you get it down to 4 decimal points? Like you have to have an intuitive sense with what accuracy can those measurements be done. If let's say generally 3 or 4 decimal points is possible, then you should present an answer which is at least down to 10 power minus 4 in tolerance. This is for absolute value, that is the quantity that you're trying to calculate without any normalization. If you just look at the successive values of x, okay, if you look at 56717 and 56714, they differ by 3 units in the 5th decimal point. So you can calculate what is the relative error. Let me do that. So if I say relative error, okay, I'm going to define relative error as the value in the next iteration minus the value in the current iteration divided by the value in the current iteration expressed as a percentage. So right now, actually I'll do it like this. I'll do it from the second iteration. This is minus this divided by this multiplied by 7.97%. Okay. So the difference between these two values, 56 and 61, is about 8%. Okay. If I look at the next row, that difference is now dropped to 0.59%, 0.5%. 0.5%. Okay. And then you can do this further. The difference between the two within 2 decimal points is like 0. But if you add more decimal points, that is about 0.0048%. Okay, now you can stop. That means you have reached your 3 or 4 significant figures. Within that, you have your value converged. You can look at the same for the other methods as well and add a column saying relative error. Relative error, the word relative means something. It means it's relative to the previous value of x. How different are 75 and 50? They are about 50% different, right? But how different are 5671 and 5672? Just one part in 10,000 parts, right? That's a very small difference. That's how you should think. So if you can define this equal to current value minus previous value divided by previous value, that is compared to the previous value, how much has this changed? So if you see here, you are already within 0.1% by 14 iterations, and by 19 iterations, it's within 1/10,000. Okay. This relative error or relative drift or relative change is an important thing that you should keep in mind as you do engineering judgments. how many of you notice that the gas prices are always around $3.2 more or less these days? You might have seen numbers like 2.7, 2.5. I remember seeing like 2.4 sometime. But in the last 2 years, it has steadily gone up because even though when they say inflation is only like 3% today, it still means compared to just 1 year ago, it's 3%. But compared to 2 years ago, it's 11% or 12%. It depends on what your baseline is. This relative always means you have to choose a baseline. And in this case, the baseline is always the previous iteration. Compared to the previous iteration, how much is it changing? So by saying it is changing by 0.01%, you're saying it's practically not changing. So there is no more gain to iterating further and you can stop. Okay. So in addition to this number of iterations, you can also report at these iterations, what is the relative error in X? The relative error in this case is minus 0.00. I'll call this 2%. Minus 0.002%. If I take a false point, I have to again add that relative error equal to current minus previous divided by current times 100. 88%. Wait, that doesn't make sense. I4.
Wait, you said it was part of the current.
No, wait, hold on. Let's start over. Again, I picked the wrong column. So it starts at 6.6% and is soon 0.001%. 0.0001%. Okay. Newton-Raphson, it converges in two iterations. So it's pretty simple. It's this minus the previous value divided by the previous value times 100. 0.1469. 0.1469%. And then what else? Secant. Yeah, we already did secant. 0.0048%. Minus 0.0048%. So some concluding remarks before I do examples, okay? If you were to select a numerical method, that is, if you're given a problem to solve and you're writing you're working on a solution that is multi-step and this is one of the steps, what numerical method would you choose and why? I need some responses.
Bisection because it's intuitive.
Bisection because it's intuitive, okay? Any other responses?
The Newton-Raphson is pretty quick.
Sorry?
The Newton-Raphson.
So you would pick that?
Well, I mean, you'd have to have an initial value, I guess.
You are an engineer, take some decisions, would you?
Yes, I would think so.
And why?
Because the number of iterations is pretty concise. You don't need to do that.
Fewer iterations or least iterations. Any other choices? And why?
I do false point because it's still fast, but its relative error is low.
Very small.
Okay, so false point because fast but also small relative error. Okay, any other choice? There is one more choice remaining, or you can make the same choice but for a different reason.
Newton-Raphson only if the functions like you easily differentiable, but secant is not.
So secant is sort of like a generalization of Newton-Raphson because you don't have to worry about computing the derivative. That's one step less work you need to do, right? So all these are very valid reasons. There are also some pitfalls to these methods, okay? Secant method has a finite chance that if you choose your interval incorrectly, or if during your iteration, if the root falls out of the interval containing the root, this could diverge. Okay, so I'm going to write could diverge if the intermediate values fall outside. I don't need this for some time. So I'm adding some remarks here, okay? So for secant method, I'm going to rewrite this, could diverge if an intermediate value falls out of the range containing the root. The only difference between false point and secant is that in false point, you forcibly make sure that the root always is contained by that interval. Whereas secant, you don't have that check. Secant is automatically, okay, you can see that here. So in secant method, what is the next value of x? It is automatically calculated, sorry, it's automatically calculated. It is automatically calculated based on this formula, and this value is put right here, this value is put here, this value is put here. There is no judgment here. You just get what you get and you keep iterating until you meet your convergence criteria. Whereas in the false point method, you do this judgment. By judgment, I mean putting this if statement and make sure the root is contained within this interval. So false point method has no chance of divergence, and for the same reason, it is also true of bisection also. So with bisection, you get a method that converges slowly, but will surely converge, and is also very simple, like was pointed out. It's the easiest to implement. But when you are doing programming for an application or for creating a product, it involves being competitive. You don't necessarily have to go for the easiest. You want to go for the things that is most accurate, most reliable. So this, even though bisection has this advantage, that's not really a big advantage because you could definitely take some effort to do the programming. False point has no chance of divergence. Secant is faster, but false point is more reliable. There is a trade-off right there. Okay. Newton-Raphson is the fastest, but what? What's the problem with Newton-Raphson?
Quite large error.
Sorry?
Quite a large percent error.
That, and you also have to compute the derivative. When you are implementing this in a computer or as a program, it's not as simple as doing it in Mathematica or with your hands, like doing the differentiation. You have to actually write a program to get the functions derivative, but the secant method is a best implementation because it approximates the derivative as the slope, as the local slope. Okay, so Newton-Raphson, if the function can be easily differentiated. Can you tell me examples of functions that are easy to differentiate? Most easy to differentiate and implement? Polynomials. If you know a polynomial, you might as well say what are the coefficients of its derivative. It's straightforward to write down. Okay. Only in such special situations, Newton-Raphson is sort of the winner. Generally speaking, secant method has an edge in terms of easier to implement. It has a good convergence rate and its relative error is also acceptable. So considering all those, it could be a winner, but it has one major pitfall that it could diverge during the solution process. So the way to kind of have a rear guard for that is to get an answer using the secant method and then do a back substitution. If you think 5671 is your answer, you have to substitute it back in the original equation to ensure that they both check out. Okay, so those are my recommendations on how to choose a numerical method. But that doesn't mean I'm going to hold your hand and make you choose something. What you choose, you have to justify both in the homework and in the exam. What are the reasons for which you chose a particular method? Okay. I will leave always a space for you to record a statement like saying the answer is this and this to within this tolerance using this method, which comes with these advantages and limitations. It will never be just write a number and get score for it. It will be always making judgments. Okay. Any questions before we do examples? Yes.
So will our exam be like the homework where you give us a function and you say do each method and evaluate each method?
No. In the exam, it will be only giving you a problem and asking you to solve it and present your answer. You will be given freedom to choose which method you want, or you will be told to use a particular method. It will either be choose your own or use this method. Like that. Okay. So for your exam, which is scheduled on September 26th, there will be 4 problems, 2 problems from this module and 2 problems from the next module. Okay, and those 2 problems will look similar to your homework problem. It will be a word problem. You'll have to read some physics, distill some equation, figure out what to solve and then solve it. Okay, so now we have about what? Half an hour. Let's try to do one example. Okay. Like the homework. So I want you to review figure 6.9. So this summary is given in figure 6.9. Okay, later review that figure. So to practice problems for your exam, do problems from end of the chapter 5 and 6. Those are like solve equation 1 and so on. But you also need to focus on the case studies, which is in chapter 8. The chapter 8 has problems which are basically like beam bending problems or fluid flow problems or heat transfer problems, something that has an engineering or a physics connection. That is what you're going to get in the exam. You will never get an equation like this and asking you to solve for x. That won't happen. Okay, so don't expect something like this. All right, so let's try something that's reasonable for the start. Maybe problem 8.13. Oh, maybe I don't know if it's the same problem. Those who have the textbook, I'll read the first line, just confirm if it's the same. The pressure drop in a section of pipe can be calculated as delta P equal to something. Is that what you're seeing as problem 8.13? Right? Okay. I have a different edition, but this is chapter 8. It should be around page 220. Thank you. Problem 8.13. Actually, I have the book here in PDF form. Maybe I can see that here. So I have the book. All right. So now let's go to 8.13. Let's since time is running short, we'll discuss this section, problem section 8.4. Okay. All right. Have all of you or most of you taken fluid mechanics? You can't get here without fluid mechanics, can you?
Yeah.
You can, but nobody has.
I haven't taken it.
Okay, so maybe this is not something you will, this is something that will come up at the end of the semester. But the idea is this. If you have a pipe flow problem, usually the first thing we do is calculate Reynolds number based on the flow velocity, the pipe diameter, and the viscosity of the fluid and the density of the fluid. For this class at least, it's not about the fluid mechanics, it's not about the heat transfer. I'll give you a formula, I'll give you the values to punch in. All you need to do is put it in the formula. Okay, so you won't be quizzed on Reynolds number and ask you to find out the formula. That won't be the case. So don't get scared. Okay. So we'll tell you what each of the values are, and if the Reynolds number is above a certain value, in this problem or in this case, the flow is turbulent, and if it's a turbulent flow, the friction factor is given by this ugly equation. Okay, you need to calculate friction factor, which is given by this equation. So look at it like this. Call your F as X, X being the value you want to solve. This epsilon, this D, and this Reynolds number, they are all known values. They come from that particular application or situation, and you have to calculate them, put them here. So I can abstract this equation down to write something like this. Because I know the epsilon, the diameter, the Reynolds number, all known numbers, or they can be calculated. This is like writing 0 equals 1 over square root of x plus 2.0 times log to the base 10 epsilon divided by 3.7 multiplied by d. I'll call it a. It's a number. We'll just call it a. Okay, call it a. Plus I have b over square root of x. This is the equation I need to solve. Okay, so the first part where you think about the so-called engineering problem is to read the problem, make sense of what these symbols are. The values will be provided. You will not be asked to exercise any judgment. Just use this value. If it's a fluid mechanics class, I would actually ask you to decide or exercise judgment on these values as well, but not here. So once you set this up, in this case, let's make a simple example. Let's say A equals 1 and B equals 1. Okay, so you have 0 equals 1 over square root of x plus 2 times, and for simplicity, I'll just make this natural log so that we don't have to, struggle too much. Solve for x. And if this is an exam problem, you're given this problem statement from which you distill this equation. If I leave it to your judgment to use whichever numerical method, what would you pick based on our discussion just now? Would you do, let me ask some questions. Would you do Newton-Raphson? No, Newton-Raphson, computing the derivative seems like a lot of work. The best programmers are also the lazier ones. Try to see how to minimize work. Okay. All right, so no Newton-Raphson. What else?
It'd probably be easier to use bisection. Because you could just plug and plug.
Yes, and you do 25 iterations and stay there and do none of the other problems. See, in an exam, it's also a race against time. You have to select something that will get you an answer sooner. Secant's probably your best bet, except you have to watch for divergence.
When you
Okay.
say watch whatever divergence, is it like you graph it and then just like know where it should be?
Yep,
So make sure-
always start with the graphical method, even if I don't say it out aloud. That is a standing instruction. Start by graphing it to see where this function might actually cross the axis. Then you have almost like 80% of the, you know it's around 0.5. If you are getting an answer like 4.1, you know you are heading the wrong direction. Right? So step one, thank you. Graph the function. Obviously, this function is not defined near zero. Okay, you need to just find enough information to know where the root may be. Okay, and also think about what this quantity is actually representing. Friction factor, if you know fluid mechanics, or if you have this information wherein you can actually plot g of f, that is, they are calling this function g of f, okay, this right side, and here is a plot of it. And you can clearly see where the root is going to lie. It's around between 0.02 and 0.3. So now you have almost no excuse from here on to give me a wrong answer. Right? You already know the answer. So now start with your secant method. You can give two interval values. You can start an initial guess, something like 0.02, and watch the answer go towards this something just short of 0.03. If it's going the other way, that's a problem. Or if it's overshooting, that's a problem. You just have to know where the answer is. Roughly, yeah.
How often would the secant method diverge?
If you start with a very initial guess that is very far from your answer expected value, it could diverge. But I don't have an example right away to tell you. But it's not about often, it's about watching for it. It's not like there is no randomness here. You make a bad guess, it will diverge. Yeah. All right, so graph the function, which tells us x is roughly around 0.02 to 0.03, and choose a method. See, there is nothing wrong in choosing bisection or Newton-Raphson. I'm not making a campaign for secant method here. It's about if it's your exam, you are trying to maximize your score. So how will you minimize time? If you are building a numerical method or a program that has to do hundreds or millions of operations each second, doing the bisection method will only make your speed go lower, which in research, it means more time to solve the same problem. Or if it's industry, it's more time or less performance with the same investment. Think like an engineer, you have to think about speed and accuracy. Right? So choose a method and also tolerance and relative error requirements. Okay. So if I leave it at this, that is, if I leave it here, I'm very sure all of you can solve this problem. What you need to get some practice on is reading the problem statement and coming up with a strategy. So you have like 80 minutes for 4 problems. That's 20 minutes per problem. So you have to think of how can I solve this problem in about 20 minutes or under. Okay. So let's look at this problem 8.13. It's the same problem. Let's try to set up the equation, and then I think by the time we'll be out of time. So read it, please. Read the problem 8.13. Pressure drop in a section of pipe can be calculated as delta P equals F, the friction factor, multiplied by length, density, velocity squared, divided by 2 times the diameter. At least remember, reassure yourself, all these values will be provided to you in my course, in my exam. Okay. Where you are given the explanation for all the symbols. For turbulent flow, the Colebrook equation provides a means to calculate the friction factor. The way when I see these problem statements, I try to strike off things that are irrelevant to the problem solving. The fact that this is called Colebrook equation has no bearing. You can call it Westbrook equation for all you care. Provides a means to calculate the friction factor. Okay, fine. You have an equation for friction factor, except it looks non-linear. On one side you have this friction factor, on the other side you have the log of the friction factor. So you already know that there are other symbols appearing, but you should also know that the next line says epsilon is the roughness and Re is the Reynolds number defined as this. So if I tell you what the roughness is, what the density, viscosity are, there is enough information to get epsilon, D and Re. Okay. Right. So the equation is now set up. After reading the problem, you have the equation set up here. What does part A say? Determine delta P. It doesn't talk about determining F. It doesn't talk about friction factor calculation. It directly says calculate delta P according to the first equation. So I will be looking for delta P, not for friction factor. Of course, there will be partial credit for getting every step right, but I'm looking primarily at the end for delta P, which involves you putting the friction factor in and multiplying all this. So I'm sure you won't be offended if I expect you to know multiplication, right? So we need delta P for a 0.2 meter long horizontal stretch. What is 0.2 meters here? That's the length. Okay. And density is given, smooth drawn. Okay. Smooth means roughness, or roughness is already given to you. 0.0015 millimeters. Velocity is given, diameter is given. Use a numerical method to determine the friction factor. Note that for smooth pipes with Reynolds number less than 10 power 5, a good initial guess can be obtained using the Blasius formula, which is given right here. So they are also giving you help to start your solution process. Repeat the computation but for a rougher commercial steel pipe with a different roughness. Okay, so it's not all that bad. They also tell you what's the good initial guess instead of doing graphing. If this statement weren't here, I recommend you to use the graphing method. You feel equipped now to tackle these type of problems? It's just about common sense. Okay, it's not too much asking too much from you. Just asking you to do read the problem statement and make sense of physical quantities. Okay. Any question? Yes.
So if we were like trying to find the real roots, to find your F and your version.
What do you mean real?
Or to find, if you're solving the function to find F,
Okay.
then you would need to set it, that equation equal to 0, yes?
Yeah.
Yes, okay, so you would just subtract the
Just
one
take
side or
this,
the other?
take this to the other
Okay.
side, that's what we have here.
Okay.
I can actually go through the motions of solving this. But if I discuss one more physical example, it would be better, I think. Like we talk about heat transfer or beam bending or something. Okay. All right, this looks long and complicated. So let's see. The equation of state is given by P equals RT divided by volume minus B, a constant, minus A divided by volume times volume plus B times square root of temperature. You know PV equals RT, that we all know, ideal gas equation. So you all taken thermodynamics at some point. So you know that this is sort of like a modified equation of state. Okay, where all the symbols are explained, R is given, temperature is given, pressure is given, volume of specific volume is given, parameters are given, and PC is the critical pressure, TC is the critical temperature. Now, one suggestion which has always been useful in my teaching is pay attention to the units. That they will always guide you to the correct answer, but at least keep you away from the wrong answer. The R is given on a per mass basis, kg or kilojoules per kilogram Kelvin, and all these values here, specific volume is meter cube per kg, so that you know what system is being used. It's a per mass system, not a per molar system. Okay. All right. So you have A and B. You can have all these fancy symbols, but the point is you need A and B because they appear here. Pressure, temperature, specific volume. Those are the three quantities that can change in a thermodynamic system. Pressure, temperature, specific volume, and they are related through this equation. That is the summary of all of this. Okay, they are related to this equation. The A and B are constants. As a chemical engineer, that's an insult to us. Okay, we'll just read it as an engineer. You are asked to determine the amount of methane fuel whose critical pressure and temperature are given here, that can be held in a 3 meter cube tank at a temperature of minus 40 degrees Celsius. Again, that's a pitfall. You need to convert that to Kelvin. If you use minus 40, you're done. Your answers will never be correct. With a pressure of 65,000 kilopascals. Use a root locating method of your choice to calculate the specific volume and then determine the mass of methane contained in the tank. So, two things here. Pressure and temperature are given. When you substitute pressure, make sure the pressure is in Pascal. Okay, it is given in kilopascal. Make sure all the units, whatever kilo or mega is given here, make sure you multiply it in so that it's easier to keep track of. The temperature has to be in Kelvin. That's a major thing. Otherwise, this equation will not work. So if you put everything in, you have pressure being a known, okay, equals RT, temperature also being known, specific volume minus B minus A times V plus B square root of T. In fact, this is not B. In my thermodynamics class, I usually call it nu, the Greek letter. It's nu, okay, but you will call it V. So then known. You need to solve for B. This is like writing some constant C1 equals C2 minus C3 minus C4 divided by nu plus a constant times square root of another constant. It's the only variable here. You have to solve for nu. Which if you do, it says use a root locating method of your choice to calculate and then determine the mass of methane contained in the tank. Here is where this course rides on a technicality. You've all taken thermodynamics. It becomes juniors or seniors. Which means you should know what is the relationship between nu and volume and mass. You didn't know that, I can't help you. I mean, you're supposed to know some basic ideas of mechanical engineering, that's all I'm saying, okay? So you need to know that mass is volume times specific volume. You need to know this. If you are able to get everything right and you are getting stuck here, the best thing I could do is make sure the partial credit is, or the amount of credit allocated for this one statement is like small number, like 10% of the total credit. It's not like if you don't get this, you'll lose everything. You might lose 10%, 15%, whatever. But you should know some basic aspects of engineering. Okay. Questions before we can talk one more example and wrap it up. So this is sort of like wrapping up module 1. The homework is due on September 14th at the start of lecture. We'll collect everything at the start. No late submissions. We don't encourage it. Okay, so please be on time, submit at the start of lecture. Okay. All right, so we have 5 more minutes. Let's think about one more problem. Yeah, I really don't like civil engineering, but if I were to pick a problem, I would, but. All right, let's try this 8.19. It's not really civil engineering. It's more like signals and time dependent functions. The displacement of a structure is defined by the following equation for a damped oscillation. You can just say, here is an equation for damped oscillation. It doesn't have to be a structure or K is given 8 exponent of minus kt cos omega t, with K being 0.5 and omega being 3. So everything is known in this function except time. Use graphical method to make an initial estimate of the time required for the displacement to decrease to 4. Use Newton-Raphson to determine the route to within 0.1% relative error or scaled error. Use the secant method to do the same. This problem is more cut and dry. You're given an equation, you are asked to calculate when will be y equals 4 or for what time y is equal to 4. Pretty straightforward. So put 4 on the other side. Four on the other side, 8 e power, what is k? 0.5 minus 0.5 times t, and omega is cos 3t. So intuitively speaking, if you have a cos wave, it looks like this. You know this. You multiply that by an exponent, what you get is something whose amplitude is decreasing, and eventually it just goes to 0 because of this damping term. You have, or you would see this in system dynamics or vibrations where you have damped oscillations. Okay, so you need to solve for 0.5 equal to this, and if you do the graphing, you can find out which is the first time, or in this case, which is the time when the value drops to 0.5. It could be here, or the way I've drawn it, it could be here, but it's some time starting from 0. Use that to have your initial guess, and then you can fine tune it with another level. Okay, so my suggestion is to go through problems in this chapter 8 or even the examples in chapter 8 and try to do as many as you can. Last thing for today. Today is 7th. On 12th, next Tuesday, after the regular lecture period, we will have a recitation session from 1 to 2 p.m. in this room. It is voluntary. There is no obligation that you need to attend. If you attend, we can discuss examples. I am not doing this because it's an official requirement. I'm doing this on my own. So you are welcome to attend. Okay, next Tuesday, 1 to 2 p.m.
Will that be recorded?
Yes, and posted. All right, thank you.